Welcome back once again to our discussion on triangles. We're working our way through right triangles. This will actually be the last video for right triangles. After this, we will get into more general triangles that don't necessarily have 90-degree angles inside of them. But here, this time, we still will do that. This time, we will get into inverse trigonometry for angles. So let's get to it. Remember from previous videos from last time that we were looking into solving a triangle. And what that meant, what that was fancy talk for, was finding all the dimensions of a triangle. All of the lengths of all the sides and all of the interior angles. So when we have all of that, we have essentially solved the triangle. Because there's only one such triangle. So for example, if I wanted to solve triangle ABC where C was a right angle, the side opposite that angle, so the hypotenuse was 10 and angle A was 30 degrees, we could find all the other dimensions. The first thing to recognize was, oh yeah, we do have two angles spoken for. All of them have to add up to be 180, so the remaining angle has to be 180 minus the other two angle measures. So angle B has to be 60 degrees. And if you want to find the side lengths, and this is actually a good general practice for what we'll be getting into next time with not right triangles, but maybe just more general triangles. You might want to take the time to actually draw out what you know and find what you don't. So let's see here. I guess this will be A here. And that's 30 degrees. You can totally tell that based on how I drew this. Thank you, resolution. But that's what we were given. And we are able now to say, oh yeah, this has got to be 60 degrees up here. And to find this side length here, which I guess is now lowercase b, and this side length here, which is lowercase a, we can do that in one of two ways. One way is to use trigonometric ratios relating 10 to this side right here. So for 30 degrees, that would be cosine of 30 being adjacent over hypotenuse. For lowercase a over here, we could use maybe sine of 30 degrees being opposite over hypotenuse. That would be definitely one way to go about finding those side lengths. The other way, right there's, I mentioned two ways. The other way I have written here. You could say, oh yeah, this is a 30, 60, 90 right triangle. So the side adjacent to 60 degrees is exactly half the hypotenuse. The hypotenuse was 10. So this side right here, side lowercase a, opposite 30 degrees, has to be length 5. And the side adjacent to 30 degrees has to be 5 root 3. Of course, if that doesn't do it for you, or if you just want to work more generally, because not everything in life is a 30, 60, 90, or a 45, 45, 90 right triangle, you could work more generally and just use trig ratios such as they are, and say, okay, sine of 60 degrees, that's opposite over hypotenuse, cosine of 60 degrees, that's adjacent over hypotenuse, and just go from there. That works as well. Of course, sine of 60 and cosine of 60, those are things we know exactly. We don't have to use a calculator for those. But had A been 35 degrees, we would have had to use the more general approach. And that's where we are right now. That's what we are capable of doing right now. I could give you any angle here, any length here, and this could be not just for the hypotenuse, but for any of the legs. And this could be any number here, although if it weren't 30, 45, or 60, we would have to use a calculator, but we could do it. We could solve any triangle given a length and a angle, or I guess actually two angles, right? One of them has to be 90 degrees. If we don't have that, we're kind of in trouble, based on what we have so far. But what if we didn't have any angles? Would we still be able to solve for things? Let's go back to the 3, 4, 5 right triangle. Right, I do have a right triangle. Angle C again is a right angle. Again, stolen from Analyze Math. And it's fair use, don't worry about it. Fair use, fair use, fair use. But anyway, we want to know all of the dimensions of this triangle. And as we mentioned before, we could use the Pythagorean theorem to find the hypotenuse. This is a right triangle, so I do have access to the Pythagorean theorem. So I could find that to be 5. But how do I get at the angles? How do I find what angle B is? How do I find what angle A is? I can say, oh yeah, the sine of angle B is 3 over 5, the tangent of angle B is 3 over 4, the cosine of angle B is 4 over 5, but what is angle B? How do I find angle B? And the way we're going to do that is to use inverse trigonometry, right? The reason we had created arcsine and arccosine and arctangent were to undo sine, cosine, and tangent. So if you could tell me that sine of an angle was 3 over 5, then if you were to take the arcsine of 3 over 5, you would have that angle. Let me show you what I mean here. Right, here's a table we had before. I've expanded it slightly to include the range in degree measure. Right, we had mentioned already that sine goes from, well, it puts in all real numbers, but it bounces on its range from plus or minus 1. Well, the inverse, we had to restrict the domain of our inputs to be just angles between plus or minus pi over 2. So we can put any number between plus or minus 1, and what arcsine would give us out would be some angle measure between plus or minus pi over 2, or from negative 90 degrees to 90 degrees, some values in the first or fourth quadrants that would give us a corresponding sine value to what input we had put in there. So if we had asked what the arcsine of a half was, it would give us the angle measure between plus or minus 90 degrees, whose sine of that angle was 1/2. And similarly, for arccosine, the outputs go from anywhere between 0 and 180 degrees, anything in the first or second quadrants. And arctangent actually has no restriction on the domain, but the range is again restricted to plus or minus 90 degrees. Now, it was not the case, not in general, that you could just do arccosine of cosine and just get exactly what you started with. You couldn't just do arcsine of sine and get exactly what you started with. They weren't true inverses in that regard. However, if your angle theta had been between 0 and 180, or between 0 and, I guess actually from negative 90 to 90 degrees, then you would actually have these properties. Well, guess what? We are in a right triangle. All of our angles, all of our acute angles of any right triangle has to be positive, and it has to be less than 90 degrees. So all of the inputs for a right triangle, the acute angle in a right triangle, will fall into these ranges, and we'll actually get these properties for free. So we can just take the arcsine of a sine and get the angle. We can just take the arccosine of a cosine and get the angle. But only because we're on a right triangle and an acute angle is what we're looking at. So let me show you what I mean here. So looking back at that 3, 4, 5 right triangle. Oh, that's a typo right there. Opposite over hypotenuse. Sine is opposite over hypotenuse, right? Sine of angle B is 3 over 5. Opposite over hypotenuse. So it's 3 over 5. But we're not done, right? I know what sine of that angle is, but if I want that angle, I could then take the arcsine of both sides, right? If you think of sine as a function, that's good. But you can also think of taking a sine of something as an operation, right? Given an equation, I could multiply both sides by a number. I can divide both sides by a number as long as it's not 0. I can add the same number to both sides and still have equality. I can subtract a number from both sides and still have equality. I can square both sides and have equality. I can take the logarithm of both sides and have equality. Well, now I can do even more. I could take the sine of both sides or the arcsine of both sides and have equality, provided that my angle is on the appropriate range where I get that property. So the appropriate angle that satisfies this now is the arcsine of 3/5, which a calculator tells me is about 36.87 degrees. So this right here is all of the new stuff for this section. Everything else works exactly like it did before on the unit circle. This is all of the new stuff right here, so let that soak in for a second. Because everything else does exactly what it did before. Right? If you had to find the sine of the arccosine of a half, well, the arccosine of a half is asking what is the angle between 0 and 180, whose cosine is 1/2. And that answer is 60 degrees. And the sine of 60 degrees is root 3 over 2. The arccosine of 225, well, the arccosine of the sine of 225 degrees, first you find the sine of 225 degrees, which is negative root 2 over 2. And the arc cosine of negative root 2 over 2 is asking, what's the angle between 0 and 180 whose cosine is negative root 2 over 2? And that is 135 degrees. So all of this works exactly the way it did before. That is not changed. We're just using degree measures instead of radian measures, I guess. That's the only other difference. But that means that we still have to handle the ambiguous case ourselves. This is looking a little beyond what we're doing in this section and more to what's happening next time with the law of sines. We ourselves have to account for the ambiguous case. Because you know what else satisfies sine of something being 3/5? 143.13 degrees. The sine of b hat here, the sine of b hat is 3/5. And yeah, we have to throw out that angle for a right triangle, because a right triangle already has 90 degrees spoken for, and 90 degrees plus 143 is definitely well beyond 180. We've definitely blown past our budget of allowable interior angles of a triangle. But what if this were not a right triangle? So starting next time, we'll have to account for not one but two possibilities, right? It could be 36.87, but it could also be 143. Not in this unit, right? Not in this section, because we're dealing with right triangles, but in next section, when we're not, we're going to have to keep track of that ourselves. So I want you to be aware of that, because that is a stumbling block. That's a thorn in the side of many a student. So I want you to go ahead and be aware of that and be considering that for when we get to the law of sines. For now, though, as far as mastery is concerned, I want you to be confident and capable of using inverse trigonometry for general angles, as I have on this slide, and also as a problem-solving tool, as I have on this slide. Those are the two things that we'll be doing in the next class. And I want to hear back from you, any issues you're having with this, any issues you're having in general. And I look forward to seeing you in the next class. You have a good evening, or afternoon, or morning, or night, which I think is a Truman Show quote, but whatever. Have a good one.